This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello and welcome back to the Neurosurgery Hub podcast. I'm Dr. Aris, Senior Attending Neurosurgeon.
And I'm Dr. Alara, Research Fellow. Today we're looking at a fascinating new study protocol from BMJ Open, published in 2026, titled STRATUM-OS, First Step in the Development and Validation of the STRATUM tool based on multimodal data processing to assist surgery in patients affected by intra-axial brain tumors.
This is a paper that I think our residents and colleagues will find particularly relevant. We've all been there, staring through the microscope at a high-grade glioma, trying to discern that millimeter of difference between hypercellular tumor and functional white matter. We have 5-ALA-A, we have intraoperative ultrasound, and we have neuronavigation. But the perfect intraoperative margin remains elusive.
Exactly, Dr. Aris. The STRATUM-OS study represents an ambitious effort by a multi-center consortium, including teams from Spain and the Karolinska in Sweden, to move beyond single-modality imaging. The OS in the title stands for observational study, and it's specifically designed as the foundational step to develop and validate a tool that processes multimodal data to assist us in real time.
Let's dive into the core problem they are addressing. The authors highlight that intra-axial brain tumors, particularly gliomas, are notoriously difficult because of their infiltrative nature. The goal of surgery is always the same: maximal safe resection. We want to improve progression-free survival and overall survival, but we can't do that at the cost of a new permanent neurological deficit.
And that's where the STRATUM tool comes in. The paper describes it as a system based on multimodal data processing. Instead of relying on just one source of information, it's looking to integrate various data streams. Specifically, the study protocol focuses on hyperspectral imaging, or HSI, alongside intraoperative ultrasound and MRI.
HSI is something our listeners might have heard about in experimental contexts over the last few years, but this protocol really aims to codify its use. For those who need a refresher, could you explain how the study intends to use HSI in this multimodal framework?
Of course. Hyperspectral imaging is essentially a non-invasive, non-ionizing, and non-contact technique. It captures a large number of spectral bands across the electromagnetic spectrum for each pixel in an image. In the context of STRATUM-OS, the goal is to use this spectral information to identify the spectral signature of the tumor compared to healthy brain tissue. The protocol outlines that they will collect these HSI cubes intraoperatively during different stages of the resection.
And it's not just HSI in a vacuum. The paper emphasizes that the tool will combine this with more traditional intraoperative data. I was particularly interested in their mention of intraoperative ultrasound, or IUS, and how they plan to register these different modalities.
That's a key point, Dr. Aris. One of the biggest challenges in neurosurgery is brain shift. Once we open the dura and start resecting, our preoperative MRI, which our navigation is based on, becomes less accurate. The STRATUM-OS protocol suggests that by integrating real-time HSI and intraoperative ultrasound, they can compensate for some of these changes and provide a more live map of the tumor boundaries.
Let's talk about the study design itself. This is a prospective, multi-center observational study. They are recruiting patients across several major sites like the Hospital Universitario de Gran Canaria, Dr. Negrin, and the Hospital 12 de Octubre in Madrid. Who exactly are they including?
The inclusion criteria are quite clear. Adult patients, 18 or older, who are scheduled for surgery for a suspected intra-axial brain tumor. This includes both primary tumors, like various grades of gliomas, and potentially secondary tumors, though the focus is heavily on the intra-axial challenge. They're looking to collect data from approximately 100 to 150 patients in this initial phase to build and refine the algorithms.
Now, for the residents listening, let's talk about the gold standard. Any tool that claims to identify tumor margins has to be validated against the truth. In this protocol, how are they defining that truth?
The study uses histopathology as the ground truth. During the surgery, when the surgeons take a biopsy or a sample from a specific area, say the suspected tumor margin, they record exactly where that sample came from using the navigation system and the HSI camera. That specific tissue sample is then sent to the neuropathologists. The STRATUM tool's predictions are then compared directly to the pathological diagnosis of that specific coordinate.
That's critical. It's the labeled data approach. If the HSI says tumor and the pathologist says tumor, the model is on the right track. But they aren't just looking at the diagnosis. They're looking at the whole multimodal pipeline. Dr. Alara, what can you tell us about the data processing side mentioned in the protocol?
The authors describe a sophisticated pipeline. They are using artificial intelligence, specifically deep learning models, to process these massive HSI data cubes. Because HSI data is high-dimensional, you can't just look at it with the naked eye and see the margin. The STRATUM tool is being designed to take the HSI data, the ultrasound images, and the preoperative MRI, and then output a simplified classification map for the surgeon.
I think it's important to emphasize that this specific paper is the protocol. They are setting the stage for what comes next. They mention that this observational step is vital for validation. They aren't letting the tool drive the surgery yet. They are observing, collecting, and seeing if the tool's retrospective opinions match the actual pathology results.
Right, and the paper discusses the multimodal aspect as a way to overcome the limitations of HSI alone. For example, HSI is a surface imaging technique. It only sees a few millimeters into the tissue. By combining it with ultrasound, which can see deeper into the parenchyma, the STRATUM tool hopes to provide a three-dimensional understanding of the resection cavity.
One thing that stood out to me in the methodology was the mention of the surgical workflow. We all know that if a new technology adds 45 minutes to a case or requires us to move massive equipment in and out of the field, it's going to face resistance. How does STRATUM-OS address the intraoperative time?
The protocol actually specifies that the HSI acquisition is designed to be fast, taking just a few seconds to a minute per scan. Since it's non-contact, you don't even have to touch the brain. The researchers are very focused on making sure this tool integrates into the existing neurosurgical workflow without significant disruption. They want this to eventually be as routine as checking the microscope.
Let's talk about the ethics and the safety mentioned in the study. Since it's observational, the clinical decisions are still made using standard of care tools like 5-ALA-A or standard neuronavigation. The STRATUM tool is essentially listening in on the surgery.
Exactly. The surgeons are not yet using the STRATUM output to decide where to cut. This ensures patient safety while the tool is being trained. The primary outcomes they're looking for in this OS phase are the diagnostic accuracy, sensitivity, specificity, and the area under the receiver operating characteristic curve for identifying tumor tissue versus healthy brain.
It's also worth noting the diversity of the consortium. We have neurosurgeons, radiologists, pathologists, and engineers from the Institute for Applied Microelectronics. It's a truly interdisciplinary approach, which is really what's required when you're dealing with something as complex as hyperspectral data processing.
Definitely. And the long-term goal mentioned in the protocol is quite inspiring. If STRATUM-OS is successful, the next step would be a clinical trial where the tool actually assists the surgeon in real time. They envision a monitor in the OR that shows a color-coded map of the surgical field, red for tumor, green for healthy tissue, and perhaps yellow for that gray zone of infiltration.
That gray zone is the holy grail. If we can accurately identify the infiltrative margin of a grade 4 astrocytoma in real time, we can fundamentally change the extent of resection. The paper also touches on the potential for this tool to be used in low-resource settings eventually, because HSI cameras are becoming more portable and don't require the expensive fluorescent dyes that some other methods do.
That's an important point for global neurosurgery. Now, before we wrap up, Dr. Aris, what is your main takeaway for the residents who might be reading this protocol in BMJ Open?
My takeaway is that the future of neurosurgical navigation is multimodal. We are moving away from the era of static images, the MRI from 3 days ago, and moving towards dynamic intraoperative data. This STRATUM-OS protocol is a roadmap for how we validate these complex AI tools. It's not enough to have a cool camera. You need a rigorous, multi-center protocol that correlates imaging with the gold standard histopathology.
Well said. It's about building a bridge between engineering and the operating room. The STRATUM-OS study is that first stone in the bridge. For those interested, the full protocol is available in BMJ Open, and it lists all the technical specifications of the HSI sensors and the statistical models they plan to use.
It's a great example of how to design a high-quality observational study. Thank you, Dr. Alara, for breaking down the technical side for us.
My pleasure, Dr. Aris. It will be very interesting to see the results of this validation phase in a few years.
Absolutely. And that's all for today's episode of the Neurosurgery Hub podcast. Keep an eye on those margins, and we'll see you in the next episode.
Thank you for listening.